Alright, let's take a look at binomial distributions again. We're talking about bottled water. 21 students in a class tried this experiment. We're assuming that students could not tell tap water from bottled water. That it's essentially guessing. And we say there's a 1/3 chance of being correct. Let x equal the number of students who correctly identified the cup containing the different water. Why is this binomial? Ooh, to check binomial, you got to check your bins. So bins means success. Is it either a success or failure? And the success is correctly identifies and man, it's not showing up. And incorrectly identifies. So yes, it does pass that first part. The second part is that independence. One student's result shouldn't tell us anything about the next student's result. So I'm definitely going to give that a check for independence. Number 21 students. And then what's my success rate? It is 1/3. Therefore, since it's 1/3, sure enough, this is indeed a binomial distribution. So we need to find the mean and the standard deviation. Well, we said our n is 21 and our p is 1/3. So to find the mean of x, we're going to use our formula, 21 times 1/3. So that says if we repeat this many times with 21 students, then the average number of students who get this correct should be about 7. Our expected value is about 7 kids getting it correct. And then what we will go ahead and do and if you actually do that math, it's 2.6. So that means the standard deviation is if we repeat this many times, the number of correct identifications would typically differ from 7 by about 2.16, either above, below the mean. So our standard deviation 2.16, our mean is 7. The last thing it asks you to do is says hey, 13 made correct identification. So you convinced that students can tell the difference between bottled water and tap water. Justify your answer. So what we're looking at here is we want to know what's the probability that that we actually get 13 here. How likely is it that 13 or more of these students actually guess it? So that's essentially what we're looking at here. And this is going to be the same thing as writing it like this. And this way we could go ahead and plug it in the calculator. We could do a binom cumulative density function with the number of trials being 21, the probability as a third, and finally our x value as a 12. And essentially what this ends up giving us is 0.9932. So if we do 1 minus 0.9932, we get 0.0068, or 0.68% chance that it's a less than 1% chance that that many students actually get it correct. So since it's less than 1% chance just by guessing, then that means that there is a strong evidence, there's a strong indication that these students truly can tell the difference